Okay, thanks a bunch. Okay, so yesterday I just tried to alert you to the existence of the stochastic area operator, and then show you if you believe it existed, we could express all the Tracy-Widom beta laws in terms of the hitting probability of a simple diffusion, a simple random ODE. At the very end, I was showing that we can actually use these things to get some quantitative information. For those in the audience that like formulas, right? We can get some formulas. For one of the bounds, we just use a cheap test function in the variational principle. For the other bound, the lower bound that I didn't get to, you have to use the Riccati diffusion. That's a more flexible object. So those slides are online, so I won't go back there. I'll just forge ahead. So today, what I want to do is actually try to prove for you. There we go. So, show that the stochastic area operator really makes sense, right? That it really has discrete spectrum, or at least give you an idea of how the proofs go. And then show that, honest to God, these beta Hermite matrix models, which you'll remember are these guys with normalized Gaussians on the diagonal and these descending sequence of chi's normalized in the same way on the off diagonal. And then if you take that tridiagonal matrix model and scale it the way you scale Tracy-Widom, that in some operator sense, which will be made really precise soon, that you really have convergence to the stochastic area operator. And then to hopefully get to some payoffs for other ensembles that you can get away from this beta Hermite thing. Okay? All right. So now, I already kind of advertised that we're going to really understand the stochastic area operator through its quadratic form. And the Tracy-Widom beta law, the negative Tracy-Widom beta law, will be defined as the ground state eigenvalue for that operator, which means it'll be the infimum of this quadratic form, right, with this certain nice positive density that's h1 norm plus a moment, and now this random quantity, right, the stochastic integral. And you got to minimize or take the inf over all f satisfying these conditions. Dirichlet boundary conditions, just normalize L2, and then you want the good part of the energy to be finite, right? That's your alp. I want to show you that this thing makes sense. And I did mention yesterday that just a stupid integration by parts doesn't work. On the other hand, all you can do is integrate by parts. So you want to beat this dB, which is a bad object. This means you have to integrate by parts in a slightly more clever way. And the idea is the following, we had lots of ridiculous ideas along the way, but what gets the optimal result is the following point of view. The infinitesimal of a Brownian path is hard to deal with, but if you could replace the dB with a delta b, with a real increment, that's a much tamer object, all right? So this is actually what you do, is you just, I always push the wrong button. So you take your Brownian path, and you decompose it as its running average plus the error. So b bar is just a little average of the Brownian path, starting at x, the integral from x to x plus 1 of the Brownian path. There's nothing holy about choosing 1, right? Just a little running integral of Brownian motion. And then you just write the Brownian motion, which you're going to stick into this stochastic integral as its average minus the error you made because you don't actually have the average, right? And then you write out what you get. So that this is just notation for the stochastic integral. I'm thinking of the white noise, if you like, as a multiplication operator. Hit it against f. Hit it against f on the other side and integrate. Okay? So if you follow this through, you have this object, right? Which is what? Which is really the derivative of the average is simply Brownian motion of x plus 1 minus Brownian motion of x. And that's what you're trying to accomplish. You're saying, I'm trying to replace delta b, dB with delta b. There's your delta b, okay? If you stop there, life would be great, but you can't stop there because that's not what you have. So this is the error to that. And that error you integrate by parts, all right? So this is an absolute equality, almost sure equality, for at least, again, for f smooth and compact support. All right? And we use this idea, and we get this random inequality that works for all functions, that holds for all functions in that Sobolev space L. All functions that are in H1 plus a moment. So here's how it reads. You pick any little constant you like. C, I'm going to use little letters for deterministic numbers and big letters for random numbers, all right? So you pick any little constant C you want, and I can bound this stochastic integral by this kind of Sobolev norm plus a random constant times the L2 norm. Now this random constant, I mean, I don't have much control over it. It depends on the C you choose. It depends on the Brownian path in some way, I don't know. But it's almost surely finite. Okay? And this is how it works. So again, you do this trick. You try to replace the dB with the delta B by replacing Brownian motion with its average. And then what you use, the reason just integrating by parts in the most immediate way doesn't work is because at some point you have a Brownian motion square, and you try to hide that under the potential for stochastic area that's just linear, right? But the squared Brownian motion grows faster than x, right? But an increment of Brownian motion grows very slowly. The increment of Brownian motion as a process only grows logarithmically. So here's a little exercise. It's ugly to unfold, but check out what's happening. Saying if I take Brownian motion, a little increment of Brownian motion, Brownian motion of x, subtracted off by Brownian motion of x plus y, and even if I soup over all y in a finite range up to 1, and then I soup over all x for all time, that this thing only grows logarithmically, in fact, a square root of log. Right? So this random object is bounded by a constant. It's a random constant, right? So it's almost surely bounded. That CB is almost surely finite, right? And this
law of iterated log.
Well, it's like a law of the iterated log for this difference, right? That's exactly the problem. If you didn't have the difference, if you just had Brownian motion, right? On the bottom you would have x log x, and that's too much for us. But if you replace the Brownian motion with its increment, then this only grows logarithmically. You lose the polynomial power, okay? And so, this thing, the derivative, yes, of b bar is exactly what? Well, it's exactly such an object. So this thing only grows like log, a random constant times log, yes? And you can certainly fit that under x, okay? And then you can Schwartz this object, and you have an f prime squared, which you can fit under this, and then you get another f squared times this object squared. But this also grows only logarithmically, so you can fit him under x too. All right, this is the idea. And to prove this, all you need to know, you don't need to know anything about Brownian motion, before today. If I just tell you the Brownian motion is independent homogeneous increments, so every increment of Brownian motion looks the same, and in fact it has a Gaussian distribution, and okay, you got to look up something on Wikipedia. The probability that a super Brownian motion on a short interval also has Gaussian tails. Those two ingredients will give you this little lemma. And then we'll give you this inequality, which first you prove for smooth functions of compact support, and then you take limits. This holds for all functions of the class you want. And what does that mean? What's the payoff here? Okay, and we're going to throw in some notation. So we have this space of functions that we're trying to identify, define this quadratic form over.
Can you say a little bit about this statement comes by very rapidly for people that are not probabilists? Can you go back a slide?
I can.
There is a C of B less than infinity almost surely.
Yeah, with probability. So you pick any C you want to put here, any little c, 10 to the minus 23rd, right? And there is a random variable. It depends on the Brownian path, and it depends on the C you pick. But omega by omega, it's finite. With probability 1, it's a finite random variable. So this is like a Sobolev inequality type thing, but the constant.
It is not, though, uniformly bounded.
It is not uniformly bounded.
For each realization of the random process,
it's whatever.
It could be enormous.
And it almost surely is. Yeah, okay. Absolutely, right? Okay. But it's really kind of the best one can hope for, and you'll see it's all we need. Does that make sense, though? Yeah. So here's kind of the point of this whole philosophy of this random operator thing is you can't compute correlations. You can't compute any distributions, right? So you have to argue path by path, right? So you get a new constant for each path, for each Brownian path, each realization of the noise in your random operator. You get a different bound. As long as those bounds are finite, right? You can argue path by path. If that helps. Okay. So let's. This is a norm squared on this space. Remember, you're going to in the stochastic area you have a gradient squared, and then you have a little first moment. So I'm just defining the natural Hilbert space that goes with that, and putting a norm on that. So this is the square norm on L, and here's what that random inequality allows you to show. Again, more big C's, right? For any little c, you have bounds above and below of your quadratic form associated with stochastic area. You can bound it by a random constant times this norm, right? And below by a small random constant times the norm minus some possibly huge random constant just times the L2 norm. Okay? By sticking in the thing from before, right? right? But bounding below, right? If you like, you have this thing, and what you want, let's go back to, maybe I should do this. What I need is I need a lower bound on this thing, how bad it can be negative. And the worst it can be negative is maybe 1/2 times this, right? Plus a huge random constant times L2. And then you feed this in here. So you have bounds above and below on your quadratic form. All right, random bounds above and below. Okay, and once you have this, now you're off to the races. Now you do the things when you look up a classical book on variational principles. And I want to extract an eigenvalue, eigenfunction out of this quadratic form. So you pick a minimizing sequence, right? So you can argue this quadratic form has, the operator associated with this quadratic form has a ground state eigenvector and its corresponding eigenvalue in the following way.
Do you care if the left-hand side is negative?
Oh, not at all. Not at all. Not at all. Right? Tracy-Widom takes negative values, right? The random variable takes negative values, so you can this thing should be able to say, and it has an infinitely long tail, right? So it should take negative values, absolutely, right? But okay, so take a minimizing sequence, right? You're taking an infimum. There is a minimizing sequence, all right, that converges to whatever it is. Now this is almost surely, again, path by path. There's a minimizing sequence, right? And it converges to something, and I'm defining this lambda tilde not. I mean, a lot of notation, but this random variable will be almost surely bounded below, because this form is almost surely bounded below, right? Again, maybe big negative, but I don't care. Okay, and now here's the deal. When you have this minimizing sequence, why do you want such an inequality? If you're taking a minimizing sequence, you have, because you're minimizing, a priori control of an H1 norm, right? An L2 norm, and a moment. So you have path by path control of H1, of L2, and a moment. So you have such control, you can at least extract a subsequence that converges in H1, converges in L2, and then you might be concerned that this subsequence, you lose mass, right? That can happen. Just because you have a sequence converging in H1 and L2, it doesn't mean that it's 0 in the limit. But it won't be 0 because you also have control of x times f squared. That gives you tightness. So you can't get mass wandering off to infinity, right? So in fact, you can pick a subsequence called fn prime, okay? And converges to some object that is going to live in L, and it converges weakly in H1. It converges in L2 properly, and it's going to converge uniformly on compacts because you have control of the H1 norm, and on the line, the H1 norm gives you holder something, like a half, right? So you have equicontinuity. So it converges to an honest-to-God function, all right? A random function, right? Omega by omega, you have this convergence, okay? All right, and then what can you conclude? The point is, now you can conclude that the infimum is actually realized, right? There is a subsequence such that this holds, right? That converges to some f naught, and you have this equality, right? We define this to be the infimum, and I'm saying there is a function at which this is realized, right? And again, this is omega by omega, but then this is an eigenfunction, right? Why is this an eigen? Because then you play the trick. I mean, just maybe this is silly to even write out, but then you have this lambda not tilde. Okay, well let's just do. Okay, fine. I'm rewriting this. Yeah, f naught h beta f naught. But this is the minimum, right, for this quantity. So if you play the game, you do something like this. You go back into this quadratic form, and you perturb. So I'm taking this f naught, which exists and it's the minimizing function. You do something like this, and this is again completely classical now, except that it's classical for every realization. So phi is some compactly supported function, smooth compactly supported function. You take a derivative, you set epsilon equal to 0. This is going to be 0 because it's the minimizer, almost surely. Right? And if you just do that and read it out, what is it going to look like? It's going to look like the eigenvalue problem, right, for H in distribution. And that's the best you can hope for because your potential is a distribution. So this is how you define the minimizer, right, and the corresponding. So what I'm saying here, that's really an eigenfunction, and then we simply declare this lambda squiggle naught is lambda naught. It's the ground state eigenvalue. And right now I'm just defining that as Tracy-Widom beta. And the definition will have bite once I show that you really have convergence of the discrete operators to the same quantity. Any questions? Yeah? Okay. Yeah. Oh, no, absolutely not. Path by path. Brown is like, yeah. So I mean, you're making a deterministic argument, but you're able to do it omega by omega, right?
But what does it mean that you eliminate tilde?
Oh, I mean, no, this is just, there was some object that's the minimizer, right? And I'm saying now we can declare it. I wanted to reserve this notation for eigenvalues proper. And I'm saying this really is an eigenvalue. There's no change, right? I'm erasing the tilde. The tilde was in case it didn't work out, right? But it worked out, so we can erase the tilde. Okay, and then, you can define higher order eigenvalues and eigenfunctions for stochastic area through, you can do Rayleigh-Ritz, right? So again, first with tilde, which we'll then erase, right? You say, I'm gonna minimize, because now I have a ground state. I have an asymptotic ground state eigenfunction, and I'm gonna take minimizers over all f perpendicular to that. But again, when I do that minimization problem, I'll have control in L2. And if I can control in L2, the minimizer of this problem will, in the limit, still be orthogonal to f naught. And it'll give me something else, all right? Okay, so
does that show you that lambda 0 tilde is bounded almost surely, or something like that?
Well, it's almost surely finite, above and below, right? It's not bounded. I mean, you can't find, right? There's not with probably one a given finite number, right? But it's an almost surely finite random variable, right? It doesn't have any mass at either endpoint. Yeah, that's what it shows. Okay, so you can go through the classical Rayleigh-Ritz thing and push the same kind of argument through and just iterate.
How do you probabilists know that? I mean, you write something down.
Well, it's this inequality. This constant is almost surely, right? The minimizer, I mean, here's the lower bound on the quadratic form. Erase this, right? Okay. And I'm minimizing over functions that have L2 norm 1. So it's just this minus, which this constant comes from that random Sobolev inequality, I quote unquote like to call it that, right? But it's almost surely, it's bounded below.
It comes back to the statement that capital C is somehow almost surely
finite, yeah.
Each realization.
Exactly. So since the quadratic form is the minimum will be, okay. Okie doke. Okay, so here's just even at this stage there's some payoffs. Okay, so this is just I'd like to tell you this. Here's some cute little things you can do. So this stochastic area operator, it's called stochastic area because you take area and you add white noise, right? So I just made a big deal about the fact that white noise is not a small perturbation of the area operator, but for large energies it kind of is. So you can rework what we had. So I'm using this curly A or cal A for the classical area operator, and you can rework what we just did to show the following, that as operators or as quadratic forms, stochastic area for any epsilon you like, there's again some random constants that our stochastic area operator looks like 1 plus epsilon area plus some big random constant times the identity here, and then bounded below by 1 minus epsilon area minus some big random constant. In the sense of quadratic forms, the same proof will show that. And then here's a cute thing. So the the regular area operator has eigenvalues that are the zeros of the area function, right? So it is known that for large K, the large K eigenvalues of area look like this, right? Now if you feed that into here, you can show the capital lambda K from the eigenvalues of random area, stochastic area, that you have the same sort of asymptotics with probability 1. So for high energy levels, random area looks like regular area. And that should make sense because you go deep into the area process, it becomes more and more regular. And this is kind of a statement of that. Of course, the low-lying eigenvalues, right, it's very random, right, because this is a big random constant, or a random constant I have no control over. But when I look at high energies, I can kind of wash that out, in a sense. And so this is a cute fact about random area. Okay.
Excuse me, can you say just once again very quickly why the epsilon is small?
Oh, I can pick it, right? I can yeah. So it has to do with, how to say this nicely. Well, it's, okay. Let me go. Where do I have the, I should write the quadratic form. But here's our quadratic form. No, that's not our quadratic form. This was poor planning. This thing I can make look like epsilon times this, right? Plus a big random constant. So above, I get 1 plus epsilon times basically the area's quadratic. Yeah, do you see? Okay, and then below. Okay. Okie dokie, sorry. All right, so now I want to get into the convergence proof, okay? And then, you know, the philosophy of how we even define stochastic array really guides how the convergence proof goes. It all goes through the quadratic form, right? Okay. So remember our matrix model, you have these, again, Gaussians on the diagonal, these chi's on the off diagonal, all right? And, you know, for a matrix, there's no controversy in defining, so I'm going to call Tracy-Widom beta n, right, the nth approximate to Tracy-Widom. It is the minimization of this matrix, right? This is, you know, there's nothing fancy going on, right? So you take your matrix, the rescaled beta Hermite matrix, and you minimize over the, whatever, vectors of L2 norm, little L2 norm 1, right? And that's the definition of the ground state, okay? And so, you know, you got to write that thing out. All right, you just gotta write what that thing looks like. And you write what that thing looks like, you know, knowing what you want, right? We want to show that this, in a sense, what we're gonna show is we're gonna show this random discrete quadratic form goes to our continuum quadratic form. So our continuum quadratic form had some, you know, H1 norm, you know, gradient f squared, plus some x, you know, plus some, you know, again, deterministic potential, and then noise, all right? So you massage things, so you get a gradient x squared, right? You want that in there, so you put it in there. And then, you know, what's going on here in all this notation, I'm just pushing the noise to the end, all right? So this a to k is what? This a to k is this beta times this thing. That comes from completing the square here. That is, you know, you need to put it in, so you put it in, you take it out. And then remember, down in the noise terms, I have some chi's. And whenever you have some random variables, you should normalize them. So you should, you know, subtract off the mean, subtract off the mean. If you subtract it off, you got to put it back in. So then I put all the deterministic stuff in the next term. All right, and this is just what you get. All right, and then you have two noise terms. One that comes from the diagonal. So the y1, the y super ones are just this process of now differently rescaled Gaussians, and then the y2 is a centered and scaled chi, which I don't even write out because it's gross, right? It's just a bunch of n's and betas and chi's that have been normalized by their means, right? But this is just what it is, all right? Okay. Okay, and then I want to look at this random quadratic form. Okay, so this is what we want to show. We want to show minimizing this, you know, matrix inner product in Rn, right, converges to this object, right, in this Sobolev space. Okay, so one issue here is that, you know, these quadratic forms live on different spaces, but that's not so much an issue, right? Because you can think of a matrix acting in L2 by taking the function that you want it to act on and discretizing in the appropriate way. And you know how you want to discretize too, because you know what the continuum scale is supposed to be n to the minus 1/3. So if now you think of your matrix, right, your rescaled beta Hermite matrix, as when it acts on a vector, you say, no, I'm really acting on functions in L2 that I've taken such that, you know, I have this function supported on the half line. I chop it off at n to the 2/3, okay? And then I break it up into little n to the 1/3 chunks, n to the minus 1/3 chunks. That gives me n chunks on the right spatial scaling. And that's really where this thing is living. And that way they're living on the same space, all right? Okay, so this is what I'm writing here. So we're going to embed this discrete minimization problem into L2 by doing exactly what I just said. You know, for any function, or I wrote it the other way. For any vector in L2, you identify it with some function, a piecewise constant function in big L2, right? And then when you think that way, all I'm doing is I'm rewriting the previous slide with these normalizations in there, right? So that gives you kind of a new normalization. So every v you see, the vk, you really want to think that looks like some f of k on n to the 1/3 times 1 on n to the 1/6. And so you're pre-scaling the vectors, right? So that's the right scaling to take. So, you know, if you're paying attention to the minute details, some of these scalings have changed from the previous slide, but it's just been put in the right space. Otherwise, it's identical. And here's what you notice. A calculation shows, so here's your gradient squared. That's beautiful. You know what to do with that in the continuum. But then you have all this other junk, right? And it's a very easy exercise to show that the running sum of these deterministic potentials go to x squared over 2, and the running sum of the noise in the potential goes to 2 on square root of beta times Brownian motion. This is classical central limit theorem. This is a sum of independent random variables. And in fact, this is the kind of thing the theorem will give you. It'll show Tracy-Widom convergence by a simple functional central limit theorem. It basically comes down to, you want to prove Tracy-Widom for some family of tridiagonal operators, you take off and you expect it, and you want to recognize this convergence through stochastic array. Well, stochastic array is Laplacian plus something. So you factor off the Laplacian from your tridiagonal matrix model, and the rest of the something you view as potential. You never prove anything converges to white noise. The way you can prove something converges to white noise is prove the running sum of it converges to Brownian motion. So if you can prove the running potential goes to x squared over 2 plus Brownian motion, you're kind of done, right? Well, you're not done, but that's the idea. So this is like, I call this an improved heuristic over Edelman and Sutton, because this is just the better place to do things. The better place to do things is at the quadratic form, and because the potential is delicate, you got to deal with the integrated potential. That's all. Okay.
So what, you sum by parts to get to these objects?
Yeah, you do a little summation by parts.
Okay. Because there's no v's in that.
Well, there's no v's, because here I'm just thinking of just potential by itself. But in the guts of the proof, you have to sum. You sum by parts because you gotta, right? You sum by parts because even at the continuum, you had to integrate by parts to be able to control the things. So
you sum those series up there by parts to get some.
Yeah, you're gonna in the proof.
Difference of the v's.
Yeah, exactly. You're gonna all this potential. You're not gonna understand this thing pointwise. It's too delicate, right? But if you do a summation by parts through, I'm saying what you're gonna get at things of this type. Right? This is the running potential up to the continuum position, running random potential up to the continuum position. This is easy, right? At least at the level of pointwise convergence in X and distributional convergence on this part. And that's the way to identify, that's the right place to identify stochastic array. Okay, but this all still needs to, you need some estimates, okay? So what do you need to do? It's the same, it's almost the same kind of thing. You need to show this discrete quadratic form is bounded below, right? All right? Again, almost surely. But now in n, right? So here is the kind of thing we prove. So yes, very much as in the proof of stochastic array, you remember this was one of our random noise terms, right? The y super 1 were just our rescaled Gaussians. We prove an inequality like this. Some small constant times, what is all this stuff? You know what that is? That's a discrete version of our Sobolev norm from before, just the appropriate discrete version, right? And then we prove, here's your L2 norm, right, on the appropriate scale, and there's a random constant, right, a random variable. This random variable depends on the little c you want to put here. It depends on all the noise terms here. Here there were a bunch of Gaussians, right? But it also depends on n. It depends on n because for each n you have a different problem. But you prove that this sequence of random variables is tight. And so if you don't know that language, this means this is a sequence of random variables that is pre-compact, meaning that it'll have subsequential limits in distribution. Okay, so at least over subsequences, it's bounded. It's bounded. Okay. Okay, and so I just wrote one down, but for both noise terms, the other noise term is the thing with the chi's. We have a similar inequality. Okay. Does what I'm saying? Any questions? Right.
Where does the Cn come from? Sorry.
Where does the Cn come from? Well, this is what we want to prove, right? So here's what it's again. Okay. So we have these noise terms that are worrisome, right? But what I'm going to prove is like I can bound them by a small constant times the good part of the discrete quadratic form plus some junk times the L2 norm, right? And when we compute discrete eigenvalues, you minimize over vectors such that this object is 1, right? But you get some random stuff, right? Some random error. But we prove, what's the statement here is that anyone could get an inequality like this, right? Just write it down. But what you can prove is that this sequence of capital C's, which are random, they're tight. It's a tight sequence of random variables, right? So it's the next best thing to them being uniformly bounded below in n, right? Because at least you'll have them uniformly bounded below over subsequences. Okay, so a sequence of tight random variables. That's just probabilistic mumbo jumbo. In probability, we have a different word for everything. Tight is sequentially compact, that's what it means, in distribution, okay?
that first sum is exactly one of the terms in the question.
Exactly. It's that first noise term, exactly. And we have an exact inequality. It's just gross to write them both out, right? But for each noise term, we have such an inequality with the same kind of C's. So what does this translate to? This translates to, I mean, it should look familiar, right? Here's our discrete quadratic form, right? Appropriately normalized. I can prove, and then that for every n you have such a thing. What we can prove is that there's a deterministic constant times the right discrete h1 plus moment norm, and then maybe a sequence of constants times the little L2 norm, another sequence of random constants above. So it's the exact analog to what I had at the continuum, except these random constants now depend on n, because you have a sequence of problems. But again, they're tight. Okay. All right, and now this is what you do. All right, because for the discrete problem, you have an honest to God, minimal eigenvalue here, an eigenvector, right? And of course, the eigenvector you're going to think about as a function, a discretized function in L2. So there's a subsequence such that so the lambda naught n is the eigenvalue for this object, right? Because of this, there's at least a subsequence of lambda naughts indexed by n prime, and the corresponding eigenvectors such that this will converge to something, okay, in distribution. And this will converge, this one is work. This is immediate from these inequalities. This takes some work, but we can show because, again, over any minimizing sequence, these vectors, you have uniform control over kind of a discrete h1 and a discrete version of the moment bound. You can show this converges to a function that's in h1 and L2. Okay. Yeah. Yeah.
Analogs of C of B, which we had
before, right? But remember now the noise for every matrix model, and the dimension keeps cranking up. You have new Gaussians, right? So it depends. It also depends on n.
Sure. And however horrible the C of B may be,
yeah,
the Cn approximates it well, and therefore they're tight.
It's not even that. It's not. I mean, you can do that, right? Because here, I mean. In the following way, see what, okay, well, you'll understand this. So this might, but what you might think you would like to do is build all the Gaussians and the Chi's in your matrix model on the same space as your Brownian motion. And then that's exactly what you would do. That's exactly the statement you would have. But you don't even have to do that because you can just show what you do is and that's what we did first, right? But then we realized what you can do is just show that sequence, you just showed by itself that this sequence that depends on these CNs that depend on your sequence of Gaussians and your sequence of Chi's, if you just show them that by itself is tight, what you do after the fact is you say Scarhut embedding, right? You say there is a probability space such that all these things live, all these Gaussians and all these Chi's live on the same space as the Brownian motion in the limit, and then you do that. So you don't have to do that extra step, but it's morally, it's the same in a sense, right? So for any at least you have subsequential convergence, right? And then of course this is work, but what you can show is that this limit actually, with all apertures summing by parts and having control of the appropriate norms, you can push through this at least along subsequences, this discretized thing will go to something, right? So, I mean, it'll go to something, I apologize. It'll go to F star hit against the stochastic area operator, go to the right continuum form, okay? And now what does that mean? That means you have this in the limit, all right? This means that your lambda star, right, and your F star are an eigenvalue eigenvector pair for a stochastic area. Of course, you could have lost, right? They don't have to be the ground. It doesn't have to be the ground state anymore, right? All this means, which you get by taking subsequential limits, is that it is some eigenvalue eigenvector pair. So you need another argument to show that it actually is the ground state, right? That you don't go up the chain of eigenvalues for stochastic area. And once you have that, then the proof is done, right? Because at this point you said, well, it just means that over any subsequence I have some limits. But now you play the game, right? Ken is the bad guy. He gives me some subsequence of operators, and I say from any subsequence of operators, I can choose a further subsequence such that this happens. So then you play the subsequence of subsequence game. So for every subsequence of operators going to infinity, I take a further subsequence such that all this holds, and there's another argument to make this an equality, and that identifies the thing. So then you can really call. Now you can really call this lambda naught Tracy-Widom beta, because it is really the distributional limit of these beta Hermite guys. Okay. So I mean, there's a lot of technical stuff in there, but that's the philosophy. Any questions? Okay, so that's the convergence proof. Yeah.
So the capital CNs, those are simple objects that you can estimate because you have Gaussians and what are the chi-squared variables?
Yeah, I mean, there's some, I mean, there's some, at some level in the proof, there's some functional of soups of Gaussians and chi's and things like this, but yeah.
I was going to ask, is it the case that actually the statements about capital C being bounded almost surely come from taking these limits?
No. The capital C, that was done at the level of the actual limiting stochastic area, and that came from.
Just making sure I understand the logic.
Yeah.
I would see a way to prove that those things are bounded by using the finite dimensional system.
But it's even better in the continuum, right? Because maybe I'm not understanding your question. Like and just proving stochastic area is bounded below, it's a similar functional of a Brownian motion.
Okay, so you guys just live in the infinite dimensional space to begin with.
Yeah. I mean, and you kind of need that, right? Because when I target this, right, I better have this thing defined somehow, right, ahead of time.
Okay.
You know what I'm saying? So at some point you actually in this proof, at some point you have to think about stochastic. You can imagine a little add and subtract. You need to be able to. You have your discrete vector, your actually nth level eigenvector, and you have to think about that thing being hit against stochastic area, with the Brownian motion in it. So you need those bounds of the continuum anyway, even ahead of time. Okay, so there are a whole wealth of ensembles for which you have Tracy-Widom convergence, and this argument can work in most of those. So just want to give you an example and then try to give you what I think is one of the better applications to this whole random operator picture. So we have these Vicious ensembles, and these are matrix models of the form MM transpose, where M is n by m and all IAD. Right? And at this point, it's classical that if you take real complex quaternion Gaussians, right, these are Pfaffian or determinantal processes. Instead of Hermite functions, you have Laguerre functions. And starting in the early 2000s, people approved Tracy-Widom fluctuations for the biggest eigenvalue, biggest rescaled eigenvalue of these Vicious ensembles. It was done by Kurt Johansen. In the complex Gaussian case, he was actually after something in ASEP. Ian Johnstone, who's an actual statistician, card-carrying member of the statistics tribe, proved it for the real Vicious case because these actually come up in statistical applications, right? So this is, known stuff. All right. On the other hand, there is a natural general beta version of all the Laguerre or all the Vicious ensembles, whatever language you like. And here's what it looks like. Again, what I'm doing now is I'm just writing down, here's a density on endpoints now on the positive line, right? Because the eigenvalues of MM transpose are non-negative. So here's a density, again, Van der Maan to the beta. Now against this kind of gross weight, right? So here's the deal. This is gonna work, this is gonna make sense for any beta positive and any kappa that's bigger than n minus 1. All right, and the deal is that when beta is 1, 2, or 4 and kappa is m, this is exactly the eigenvalue density for those real complex or quaternion Gaussian Vicious. Right? So this is a family of these are the Laguerre beta ensembles where you actually get to not just generalize beta, but generalize one of the dimensions to a real variable that if that turns your crank, right? You don't need integers in both dimension coordinates. Okay, and there is a matrix model too, a tridiagonal matrix model for all beta. This is again work of Dimitriou and Edelman, and this is what it looks like now. So to cook up the tridiagonal matrix model for the whole Laguerre, beta Laguerre family, you do the following. First, you cook a random upper bidiagonal family, which has a descending sequence of chi's on the diagonal and the off diagonal. One sequence of chi's is tied to the first dimension component, and the other to the second. Okay, all chi's appearing here are independent, right? Like even if notation gets reused if k happens to be n, but these are everything in sight is independent. And then the third theorem is if you look at BB transpose, the eigenvalues of that thing have joint density beta Laguerre. All right? Okay? And it's, a little exercise you can show yourself for any m. If m is an actual m by n, honest to God, matrix of independent, say, real or complex Gaussians, forget the quaternion case, you can find u and v such that this object, right, if you rotate m by some unitary on the left and some unitary on the right, you can bidiagonalize any Gaussian matrix by, again, the same sort of house order transformations we had before. Right? And then when you do, this thing times its transpose, right, you eat the v in the middle and you maintain the same spectrum. Right? That's how it works. Okay, so here's a theorem. It's not that exciting at this stage, but for the biggest...
It's called beta Laguerre because for this equal to this will be Laguerre.
Laguerre polynomial, exactly.
I will be diagonal. No, diagonal.
Well, okay, so there is okay, you form this bidiagonal and then you do this, BB transpose. Now that's tridiagonal. And the eigenvalues of this thing, right? Because this thing may not, all right. Or if you like, you can say the singular values of this dude are the singular values of the guy. Okay, so just, for completeness, right? If you take the ordered eigenvalues of the general beta Laguerre ensemble, right? And you form these kind of gross looking scaling constants, then the theorem is that if I center and scale any k eigenvalues of beta Laguerre in this way, that these converge to the ordered eigenvalues of stochastic area. And if there's anything nice about this, it's that the history of this problem is that somebody did it for the complex case, somebody did it for the real case. That somebody for the real case was Ian Johnstone, as I mentioned. And in his original proof, he required that the aspect ratio of kappa over n, in his case kappa was an integer, had to be bounded above and below uniformly as n went to infinity. And then in statistics, apparently there are cases where you really care about the aspect ratio either blowing off to infinity or going to zero. This comes up. So other people wrote other papers in the real case for crazy, right? And this theorem does it all in one, it's all together in one swoop.
Excuse me, Brad.
Yeah.
I'm confused with the notation problem. Say Laguerre polynomial. Let's take beta equal 2.
Right.
Laguerre polynomial ensemble.
Yeah.
Just to test such like process.
That's at the hard edge. I'm at the biggest edge.
Oh, sorry. Okay.
I will talk about hard edge. Yeah. So this is at the biggest eigen. At the smallest eigenvalue, you can get Tracy-Widom and you can get Bessel, depending on.
And do you have similar theorem for Bessel?
Yeah. We have an operator for Bessel, so that'll be tomorrow. Okay, so. Okay, so they're fine. Okay, but this isn't, I think, super exciting. This is just to show that you can work through the same kind of ideas. But here's an honest-to-God application. And it's tied to what are called these spike distributions. So Ian Johnstone, same character, asked the following question. What happens to Tracy-Widom for quote-unquote non-null Wishart ensembles? So the null Wishart ensemble is really when you have M transpose, and M is all ID-centered Gaussians, right? But for statistical problems, they care about things like this. M some sigma, which is called the population covariance M transpose, for a general sigma, right? So if you really want to base hypothesis tests on the biggest eigenvalue, on Tracy-Widom, you'd be interested in what kind of sigmas break Tracy-Widom, right? And he even asked the question, look, I'd be happy if you could do the following. Take sigma to be the quote-unquote, this is where the spike comes from. I'll take sigma just to have, instead of being the identity, C1, C2, C3, right? 3 different constants and all the rest ones, right? In what cases can you mess up Tracy-Widom, right? By putting different constants there. Okay, and this is one of these situations where I think the answer is more fascinating than the question. So in 2005, Baik, Ben-Arush, and Pech showed there's a phase transition in these problems in the spiked ensembles. And here I'm just going to demonstrate what they did for r equals 1 for one spike, right? So the sigma here, where are you sigma, is just C, then a bunch of ones. Just one, you just take one entry and you screw it up, right? So what they show, there's a critical, this is a little math frac C, right? There's a critical value of this C. It depends on the aspect ratio, on the dimensions, you can compute it. But if C is below this critical value, nothing happens, right? In the sense that you still get Tracy-Widom, right? It makes sense. You start off at 1, you push it up a little, you expect there to be some room. And I'm using the same notation. Sigma and n are the sigma and n I had on the previous slide. So same centering and scaling, same limit law. If C is bigger than the critical value, you change the centering and scaling and you get a simple CLT. What happens there, the idea is if you push that constant too big, the biggest eigenvalue actually jumps out of the spectrum, right? And just wiggles as an independent Gaussian by itself. You have the density of states, and the biggest eigenvalue actually escapes and just fluctuates in a very classical way. Okay? And then there's actually a tuning around the critical value. If you do this, all right, just say you do it. So you take C to be the critical value plus something going down like n to the minus 1/3, and then you take the limit as n goes to infinity. With the same centering and scalings, you get a new family of distributions, which depend on this extra parameter. And then new family of distributions looks like Tracy-Widom times something, and this something can also be written in terms of Painlevé 2. Right? Something that can be expressed in terms of the Lax pair for Painlevé 2. And just here, like I just want to mention, the beta equals 2 is absolutely critical, right? This is a determinantal thing. Subsequently to this, Mo did work for beta equals 1, and then there was a partial result for beta equals 4, using the analysis and the Pfaffian processes by Dong Wang. But the whole random operator point of view really makes kind of quick work of this. So the deal is you can still try diagonalize. All right, so like, again, just thinking of one spike, right? And a cute little exercise is, remember what you have now. Do I have some chalk, right? You think of M just being all IAD Gaussian, and then you take C's and a bunch of 1s, and M transpose, right? Well, take this matrix and write it as, this is silly, right? Square root of C and a bunch of 1s, and square root of C and a bunch of 1s, right? And put this one with this guy and this one with that guy. And all you do is you change one row or column of your M, depending on how you're looking at it. And then you just do the same procedure. And you can still try-diagonalize, and you get the same sort of tri-diagonal model. The only thing...
Can I ask you, why is the transition out of C equal 1 in the theorem?
What?
The transition, the transition point.
I'm not saying the transition is C, no.
Why isn't it C equals 1?
Why isn't it?
I don't. You do the work, and why does anything happen? You sit down and you prove it.
I would guess Tracy-Widom and guess Convergence principle. That's what I was thinking.
Well, I mean that's okay, but that's an interesting thing, right? It's showing that at some level you don't see the signal through the noise, right? You can be looking at an ensemble that you actually can move one. One of your vectors is not standard Gaussian; it's Gaussian with a shifted variance, and your biggest eigenvalue just doesn't see it. Right? So So I mean that actually has content for people that do PCA stuff on a daily basis. Yeah. So that's I don't know either. I mean, yes.
So just to make sure I understood, you just wrote this down, and I guess the claim is that is a parameterization of the spiked beta model.
Sure. And so then what you do is you put this guy here. You pair this guy with this M. This is a Gaussian matrix, and you bidiagonalize that. All right? And when you do that, all that happens is that you just change that same tridiagonal matrix model I showed you. Nothing changes except you shift one entry.
No, my question was before that. The statement is that with M, IID random matrix, this quantity exactly has eigenvalues that are distributed by spike to spike.
Oh, yeah, absolutely. Okay. So, I mean, you go through this tridiagonalization step, and so you get the exact same tridiagonal matrix model, except you change one entry, and then you think, well, how can that do anything in the limit, right? And it does almost nothing in the limit. So this is a result of Bloemendahl and Varag. Bloemendahl was a student of Bell and Varag. So at criticality, so I'm using this notation, right? Remember, B was our bidiagonal matrix, but I'm calling it BC, for where I shift that one entry. BC times BC transpose, when I take C to be the critical value plus this shift, this converges into the now familiar operator sense to stochastic area. The only difference is we change the Dirichlet boundary condition to a Robin boundary condition where that parameter shows up. Right? So in fact, you have a whole general beta spiked ensemble, sequence of eigenvalues. So stochastic area with maybe a different boundary condition, right? For different betas and different W's, there's a whole family of ground states, right? And by taking omega, or this W, whatever you want to call it, to infinity, that's classical, quote unquote, Tracy-Widom beta. Okay? So that's their theorem, and I won't show how that works, but let me, you can give me one more second, I'll show what I think is the best payoff of this, is the following. You can still play the Riccati game, all right? So I mean, a corollary of having Tracy-Widom was having this theorem about if I want to actually, write down a formula for its distribution function, the context to do this is like cook up this little diffusion and ask that it never explodes. It never explodes to minus infinity. And you remember what you did there is you looked at a shooting eigenfunction, right? You looked for a phi. Is that a psi? I don't know. that depends on x in a fixed lambda, satisfying your eigenvalue problem. But for the Dirichlet case, you want to start it off with at 0 and at 1. But in the Robin case, you started off at 1, psi 0 is 1, and psi prime is omega, right? That's the right shooting for the Robin case. And when you look at the Riccati, you don't start at infinity anymore, you start off at omega, at a finite place. And if you carry through what I did yesterday, the upshot is the general Tracy-Widom beta law is the probability of this little diffusion starting off at time lambda, lambda is the spectral parameter, at spatial point w, and asking that never explodes. So all the Tracy-Widom beta laws are tied to the same diffusion, just for different starting times and different starting places. And then, here's just a fundamental fact. Any Markov process, if you take any Markov process and ask for the probability that it never leaves its domain, that's a quote-unquote harmonic function for the process, which means that that probability is killed by its generator. So what you're looking at here is you're looking at P, you're looking at the spatial process, and implicitly you're looking at time. So almost immediately, it means that if you write, here I'm writing, this is the distribution function for Tracy-Widom beta, it solves this PDE. This is just the PDE that is defined to be the space-times generator of if I look at the diffusion P along with its time coordinate. That's just automatic, all right? It requires no work. So you can prove that this PDE is a unique bounded solution with the right boundary. The right boundary conditions are that you're looking for an f that's a distribution function in lambda. And then if you affix that to this PDE, you can show that it has a unique bounded solution. So that thing will be the Tracy-Widom beta distribution function. So there's much ado about how if you can get formulas for beta 1, 2, 4 and for different spiking levels and blah blah blah. But this PDE has actually been used as a starting point for Igor Rumedov to get the first Painlevé formulas outside of beta equals 6. And so Igor has this work where he gets Painlevé, it's again in terms of Painlevé 2 for beta equals 6. This is the first beta for which there's been any exact, if you like exact formulas. I mean, I would argue that probability is an exact enough formula. But if you like exact formulas, Igor's done that. But I don't know the full story. So Igor did something, and then I know that Professor Itz and Tamara cleaned some of his asymptotics up, or maybe he got something wrong. They can tell you more about it, but this has actually been used to get Painlevé formulas, is the point. All right, I know I'm over. Thank you.
So, excuse me, did I understand you correctly that it is possible to define all these, let's say, quadratic forms on the same probability space, and then just the quadratic forms would converge to the limit quadratic form, and just then the eigenvalues would be random variables on fixed probability space, and there would be just this convergence in terms of, so to speak, the operators themselves understood as the Dirichlet forms.
Exactly.
Is this correct?
That's really how the proof works. So the proof really is an almost sure statement, right? So we show with probability 1, the first eigenvalue converges. We can do it again the second eigen. And so this is all almost sure. So if you have 17 almost sures, then you can back up and say jointly in distribution. Well, yeah. Well, I mean, do for the second eigenvalue, the third eigenvalue, up to 17 eigenvalues, and every statement is with probability 1. So then you have joint weak convergence, right? Which is how we advertise it. Yes, Professor Ritz?
Maybe I have a remark.
Okay, yeah. What's the real deal?
The very last exclamation sign.
Yeah.
So the more exactly, of course, in Romanov paper, it is you have to express TW. You have to, of course, know in the function, but also you have to solve some auxiliary complicated ODE.
Okay.
And or equivalently, you can say that you can express the Tracy-Widom for beta equals 6, even for beta equal any even.
Right.
In terms of the not Painlevé but Calogero Painlevé solution. This also was shown by Romanov. But only recently, only just a year ago, it was finally shown that this Calogero Painlevé system is integrable. Integrable in the sense of it is the work of Bertalat, Rubtsov, and Kafas.
Okay.
So in a sense, it was very important step what Romanov did. But it was, we have a paper with Tamara, with Kapaev and with Andriy, when we explained that after Romanov work, it was still a lot of work we've done. And now it is sort of in the very good setting. So now indeed, at least for all even
all even beta?
even better, we can say that Tracy-Widom is indeed represented by some integrable systems.
Okay, I see. I see.
Okay, so let's thank Brian again and go for lunch.
Another narrow escape.